Good. Well, we're going to put this idea of electronegativity aside for a minute, and we're going to talk about now the structure, drawing the Lewis structure of the molecule. And then we're going to come back and pick up electronegativity and add to our structures. So we're going to talk about structures. We're going to talk about Lewis structures. Okay, Lewis structures are very helpful, and we're going to follow certain steps for drawing these Lewis structures. Now, we do need to follow these steps in order. Okay, they do need to be followed in order. Are these steps going to be given to you?
No.
No, so you're going to have to learn those, right? Yeah, okay, and we need to do it in order. So this is let's just kind of go through these, and we'll work our way through. So the first step, let's draw a structure. Well, you know what, before we actually draw that structure, I kind of want to go over some definitions. So I think that that's going to help us. So let's talk about this as an example of a Lewis structure. Carbon attached to 3 hydrogens and a bromine. Okay. So there's a Lewis structure. All right. So let's talk about some definitions. When I say a bonding pair of electrons, you know which one I'm talking about, right? It's the electrons in a bond. Okay, how many electrons are in a bond? 2. 2 electrons in one bond. Okay, so this is a bonding electron. These are all bonding electrons, aren't they? So this is one bond or 2 electrons. Now this 2 here, these 2 dots, those are going to be 2 electrons, and we're going to call that a non-bonding pair. Okay, so this is a non-bonding pair. Or another term we would use is lone pair. So I have one lone pair here, or I have a non-bonding pair here. But how many electrons, non-bonding electrons, do I have right here? 2. Does everybody see the difference? Okay, great. Now, every pair of electron, we're going to call an electron domain. Electron domain. Okay, so what's an electron domain? An electron domain is a pair of electrons. So how many total electron domains do I have in this entire structure?
7.
Yeah, can you guys count them all up? How many electron domains are there? Does everybody see that there are 7 electron domains? 1, 2, 3, 4 bonding pairs, 5, 6, 7, with 3 more non-bonding pairs. So I have a total of 7 electron domains. Make sense? All right. How many non-bonding pairs do I have? 3. Okay, how many non-bonding electrons do I have? 6. Okay, see that difference? All right, how many bonding pairs of electrons do I have? 4, but how many bonding electrons? 8. Okay, don't mix up a pair with an electron. An electron domain, what did we say an electron domain was? A pair of electrons. It could be bonding, it could be non-bonding, right? Electron domain, well, you're going to need to remember that. Electron domain means any pair of electrons. Okay, now another thing we need to know is the center atom. The center atom, we're going to call it, so since the center, guess what? We're going to call it the central atom. Okay, central atom is the one in the center. Makes sense, right? Okay. Well, how about the ones not in the center? Okay, the ones surrounding the central atom, we're going to call peripheral atoms. Okay, peripheral atoms. So that's important to note the difference, because we're going to do something to the central atom or we're going to do something to the peripheral atom. You need to know which ones I'm talking about. Okay, so peripheral atoms are the ones that surround the central atom. All right, are we good with those definitions and terms? Okay, so now let's actually draw that Lewis structure. So I would say CH3Br. That's the formula that we would get, and we would need to draw that Lewis structure. So let's go through the steps. Now, you may have used other methods before, and that's fine, but I want you to go through these steps. Even if it's a simple structure, and you could probably do that without doing the steps, You need to get used to doing the steps with simple structures, so then we start doing more complicated structures. These steps will still allow you to draw the more complicated Lewis structures, which you may not have done. So let's start. First thing, sum the valence electron of all the atoms. Okay, I have a carbon, a hydrogen, another hydrogen, another hydrogen, and a bromine. I need to add up all the valence electrons. Well, how do I know how many valence electrons there are? How many valence electrons would carbon have? Do you remember how we would do that? 4. Where'd you get 4? From the periodic table, it's what? Group 4A. Exactly, it's group 4A. So carbon is group 4A. That means it has 4 valence electrons. So let's write that down for carbon. It's 4. Well, what about hydrogen? 1. And each hydrogen has 1, right? So I'm going to put that down. And then what about bromine? What would I have for bromine? 7. It's in group 7A, isn't it? Okay, so I'm going to put 7. Now, how much does that add up to be? Right? 14. Okay, what is that? 14 individual electrons. Individual electrons. It's important to know how many there are, because when you get through with your Lewis structure, it's too often a common mistake to have more electrons. We kept throwing bonds in there than what we are starting with. We can't create matter, okay? So we need 14 electrons. That's all we're going to have. So when you're said and done, you need to make sure you've used up all 14. We didn't destroy them or create them. Now, so that's summing up the valence electrons of each atom. Now, if I had an ion that was a negatively charged, what does that mean? If it's a negative charge, did I lose an electron or gain an electron? Gained an electron. So for each negative charge, it's 1 more electron. So if it's a -2, then I add 2 electrons. A -3, I add 3 electrons, right? Okay, and same thing for the positive charge. That means I lost 1. So take away 1 of those electrons. All right, so this is how we sum up the valence electrons. So once I know how many there are, then we can proceed to draw our structure. First thing, draw the skeletal structure. What does that mean? That means I have to identify the central atom. So in this case, carbon is a central atom. It's not going to be bromine, it's going to be carbon. And we'll talk about ways, that's probably the hardest thing to determine is what's the central atom, and we'll talk about ways to do that, some helpful hints. So we're going to put carbon as my central atom, that would be carbon. And then I'm going to put the peripheral atoms around that. So that would be a hydrogen, 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 and a bromine. Now it doesn't matter where I put the bromine. I can put the bromine on the bottom, that's fine. Or maybe I want to put the bromine on the side and hydrogen on the bottom. That's fine. It doesn't matter. It doesn't matter how you arrange the peripheral atoms. Okay, so I've done that. Now I'm going to connect them with single bonds. So I'm starting to use some electrons. Every bond uses how many electrons? 2 electrons. So we're going to keep a tally. I've got 14 individual electrons. Individual electrons. Now I'm going to put in single bonds. So I'm going to connect all these with 4 single bonds, right? And each bond has how many electrons? 2. So how many electrons did I start to use up? 8. So I'm going to subtract 8 individual. Remember, these are individual. I'm not going to subtract 4 bonds. I'm going to subtract 8 individual electrons in bonds. Okay, so it's the individual electrons in a bond. Subtract 8. What do I get left? 6. Okay, next step. Complete the octet on the peripheral atoms first. Don't do the central yet. Do the peripheral. So let's take a look at the peripheral. Well, bromine here, has 2 electrons, so we would need to complete the octet for bromine. But look at hydrogen. Does hydrogen ever need 8? Do you remember? Hydrogen only ever wants 1 bond or 2 electrons. So whenever we're having hydrogen, remember, it's not going to get a complete 8. It's only going to ever have 2 electrons, the most. So when we complete the octet, we do need to remember that hydrogen only needs 2. So write down in here 2 electrons, not 2 bonds. Okay, so that's 2 electrons. Hydrogen only needs 2 electrons. So if hydrogen only needs 2 electrons, here's my 2 electrons right here in the bond. So I don't need to do anything, right? I don't need to complete that one. Don't need to do that one. Don't need to do this hydrogen. Well, let's look at bromine. Bromine, again, has 2 electrons. How many electrons do you need to complete the octet? 6 more, right? So let's put in 6. 1, 2, 3, 4, 5, 6. So I subtract 6. That leaves me with 0 left over. Okay, so I've completed the peripheral atom. Now, if I had 2 left over or 4 left over, I would put those on the central atom as non-bonding pairs. We didn't have that in this case. And then if the central atom needs more electrons, we use multiple bonds. Don't try to do multiple bonds. We'll talk about structures here in multiple bonds in a minute. Don't try to do this first. This is the last thing you do. You don't do multiple bonds until you get to 0 left over. So don't try to do bonds earlier. It's the last thing you do. We'll talk about that in a minute. So that's how we draw our Lewis structures. All right, make sense? So we got that? Okay, so let's talk about how we're going to determine that skeletal structure. That's probably the hardest thing. There's a couple helpful hints. The central atom is usually the least electronegative and can be written first. Okay, it's usually the least electronegative and can be written first. So let's look at this one. Let's do POCl3. Okay, so POCl3. Now we're looking at that. Wow, phosphorus, oxygen, chlorine. Which one would be the central atom? We're like, well, maybe it's phosphorus, maybe it's oxygen. Kind of hard to tell, isn't it? So how are we going to do it? It's going to be phosphorus, yes, because the least electronegative, so phosphorus and oxygen. Phosphorus is going more on the diagonal there. And oxygen, and it can be written first. So this is phosphorus, and then we would put the 3 chlorines around it and an oxygen, and it doesn't matter how we arrange the 4 peripheral atoms around it. Okay, that's one hint. Okay, it's usually least electronegative, can be written first. Another hint would be to try to look for symmetry. Okay, try to look for symmetry. You guys know what symmetry means? Yeah, kind of like mirror images, kind of like symmetry. All right, so let's look at this one. S2Cl2. S2Cl2. Symmetry would be sulfur attached to a sulfur, and then I could put chlorine over on one side and chlorine on the other. Is that symmetrical? Yeah. Okay, well, what if I put 2 chlorines on 1 sulfur? That's not very symmetrical, is it? Okay, so try to look for symmetry. That's another clue. Try to look for symmetry. And then another one, carbon is generally always the central atom, which we saw a minute ago. So whenever we see carbon, carbon likes to be the central atom. Hydrogen and fluorine, not so much. Remember, hydrogen has, how many electrons does hydrogen want? 2. That's 1 bond, right? Well, can it ever be the central atom with multiple bonds around hydrogen? No, it can never happen. So right here, right, fluorine will never be a central atom. And then for fluorine, hydrogen will never be a central atom. And for fluorine, put usually is not a central atom. It can on occasion do that, but usually not. Okay? So hydrogen, never. Fluorine, usually not. Sometimes it will. Okay? All right. Okay, so there's another clue. The formula is often written in order of bonding, so let's look at that one. That would be hydrogen, carbon, and nitrogen, HCN. That's in bonded, that's its order of bonding, HC and N, with carbon as the central atom, which we kind of knew that already. Yeah? All right, so there we go. So that's another one. And then oxyacids. We remember what an oxyacid is, right? Yeah? Yeah? We think so. What was an oxyacid? Give me an example of an oxyacid. It's got acid. Think of an acid. It's got hydrogen in the front, yeah? Oh, HClO. Yeah, it's got an oxygen in it, right? Okay, so HClO is an oxyacid, right? How about H2SO4? Is that another one? HNO3. Okay, starting to come back. What an oxyacid is? Yeah, H in the front, got an oxygen in there. All right, now if you're looking at H2SO4, we're thinking, hey, doesn't it look like sulfur's the central atom and hydrogen's bonded to it? I mean, it kind of looks like that, doesn't it? But in this case, it's not. So for oxyacids, we have to think. Oxyacids, sulfur, yes, is the central atom. And the oxygens are around sulfur, but not the hydrogens. The hydrogens are out here attached to each oxygen. Okay, they won't be attached to the central atom. They're going to be attached to the oxygens. And that's the skeletal structure for an oxyacid. All right, make sense? Okay, so let's practice drawing again. Let's draw another Lewis structure. This time, let's see if we have one with leftover. We got as far as completing the octet. We didn't have any leftover electrons. So now let's do one with leftover electrons, and pretty soon we'll do one with multiple bonds. But let's do PCl3. PCl3. Okay, we want to draw the Lewis structure for that. So let's sum up the valence electrons. I've got phosphorus, chlorine, and another chlorine. How many valence electrons does phosphorus have? 5. Everybody see 5? And each chlorine has 7, right? It's in 7A. Okay, so 7, 7, 7, 7, 7. So what does that add up to be? Total of what? 26. Remember, this is 26 what? Individual electrons. 26 individual electrons. So now, which do you think is the central atom? Yep, P. Okay, so let's draw that. And let's put the 3 chlorines around it. It doesn't matter where I put the 3 chlorines as long as they go around it like that. Now, I'm going to connect them with bonds. Every bond uses how many electrons? 2. So I've got 2, 4, 6. So I've used 6 electrons. So let's keep our tally going. 26 individual electrons minus the 6 individual electrons in bonds. So we're going to do bonds. And then that gives me what? 20 electrons to work with? So what's the next thing we do? Besides the bonds, we're going to do what? Complete the for the, which one? Peripheral. Okay, so you do bonds, then peripheral. Okay, so remember that order? Bonds, then peripheral. So we're going to do peripheral atoms. All right, chlorine already has 2. These are individual electrons. Chlorine already has 2. So how many individual electrons do we need? 6. Let's put 6 around here. Okay, so can I do that for every chlorine? All right, so let's put 6 dots around every chlorine. And when I do that, wow, how many of those dots did I use up now?
18.
Yeah, let's see. 1, 2, 3, 4, 5, 6 times 3 of them. I've used what? 18 electrons minus 18. And these are individual electrons around the peripheral. Okay, around the peripheral. All right, so that's next. That gives me 2 electrons left over. See, now I have leftover electrons. So let's go to the next one. What am I supposed to do with leftover electrons? On the central atom as individual dots, or as what? As a lone pair. Okay, so I'm going to put that right here on phosphorus as a lone pair. So that's minus 2 electrons. So this was individual electrons for lone central atom. So this is central atom, lone pairs. And that leaves me with 0 left over, and then that's my Lewis structure. I can double check to make sure the central atom has an octet, and does it? Yeah, it does. All right, so here's a question. How many electron domains are around phosphorus? 4 electron domains, right? What's an electron domain again? A pair of electrons. So how many electron domains do I have around phosphorus? 4. I have 4 electron domains around that central atom, don't I? Okay. All right, and that's how we draw the Lewis structure. Questions about how to do that? And we'll do the multiple bonds here in just a minute. So far, so good? Okay, well, let's see if you can do that then. Let's see if you can practice one. Let's do OF2. Now, I want you to follow these steps. Follow the steps that we have outlined here so that you get used to doing them. I know you can do this as a simple structure, and you could probably do it without the steps, but follow through the steps. All right, so see if you can draw OF2. So we're going to look up on the periodic table and find those valence electrons, aren't we? Okay, so do it through the steps. I want to see the individual steps worked out. Don't just put it together. Do the steps. Okay, because the steps are going to help us when we get to the more complicated structures. So don't just draw the structure, think about the steps. Sum up the valence electrons first. And your last lab report, by the way, is going to be doing this very thing. So if you want to, you can be working on your lab report as we go. Like today, we're practicing drawing the Lewis structure. So on your lab report, that's what you'll be doing. So that's going to be a dry lab. So if you want to, you can start working on them as we go. So you can have them all done before you get to class, lab, if you want to. Okay, so this lab report is going to be the one that's after spring break, right? Okay, so you summed up the valence electrons. Which did you identify as essential atom? That part's easy. Oxygen. All right, now we have to put individual bonds in, right? So you go bonds, peripheral atom, central atom. It goes in that order. Bonds, peripheral atom, central atom. Okay, so, woo, boy, it looks like we just all nailed this. Awesome. Okay, so you're adding them up, yeah? Fluorine has 7. It's in 7A, and this fluorine has 7, and this oxygen. No, don't put them in. Just add them up. 7 plus 7 plus 6. What? Right? We add them all up, yes? What do you got? 20? Okay, now put in the, what did we say? Bonds are next. So draw the bonds in. How many electrons is bonds? So subtract 4. Okay, keep going. You do bonds, then you do peripheral atoms, then leftover on the central. After you've added them all up to get there. Yes?
Okay. I have 4 left. Do I put 2 here, 2 here?
Perfect. Okay, how are we doing, you guys? Oops, getting it? Awesome. It's okay. It's okay. How are you doing? Good? All right. Awesome. Okay, it looks like we got it, right? What do you think? Is it making sense? Did everybody follow through those steps? All right. Maria, how'd you do? Good? Yeah. Yeah, some of us might like this a whole lot better, huh? How are you guys doing all over here? Easy, right?
Yeah.
Just stepped right through it.
Can we use a double bond for her?
No.
Okay, easier, but I was trying to
Nope.
see if it's gonna
Nope.
work.
Mm-mm. Because you can't do that. Think about it. This has 2, 4, 6, 8. And did you add up all these? This has 8, that has 8, that has 8. So why would we need double bonds? Because then that's going to give us more than an octet.
Right here, it's still gonna be 8.
Yeah, how many electrons do you have all added up all together? 20? So count that and tell me if you have 20.
2, 4, 6, 8, 12, 14, 16.
How about that? You destroyed matter in the process. So are you going to do the double bonds?
That's right.
No.
That's a big X in there.
No. Instead, we're going to do this one and follow the steps, right? Don't create or destroy those electrons, right?
You can't do that.
You can't do that. Yeah.
Doing experimental things.
Okay, does it look like that? Now, you could have drawn the fluorines on each side, but you didn't have to. You could have put one on the top and one on the side. That's fine. Or you could have put a top and bottom. That's fine. Doesn't really matter where you put them. You could have put fluorine here and a fluorine there. That's okay, too. All right, so you've got the fluorines, and then you got a single bond, right? Then you completed the octet. Okay, so that was 12 around there. And then you had 4 leftover electrons. And where do the 4 go? On the central atom in pairs. Yay! Awesome! Awesome! Okay. All right, well, let's do one with multiple bonds. Yay! All right, so let's do CO2. Let's go through that one. All right, so we're working our way down. Now we're going to see what it's like to do one with multiple bonds, like double bonds or triple bonds. All right, CO2. So carbon is what valence number? Valence electrons of what? 4. Let's put that up. And then each oxygen has 6. Okay, so all together I've got, okay, so 6 and 6 is 12, plus 4, yeah, 16 individual electrons, right? 16 individual electrons. Okay, so let's do our bonds. Carbon is the central atom, oxygen on either side. Draw the single bonds. How many electrons did I just use up? 4. So that's minus 4 individual electrons in the bonds. Then what comes after bonds? We do what? Peripheral. Okay, so let's complete the peripheral. What does oxygen need? What does oxygen need? 6 more. Okay, so let's put 6. Same with the other oxygen, right? Okay, so how much did I use up there? 12. Okay, minus 12. And that was the peripheral. And then I have 0 left over. So there are none that go on the central atom. Now let's double check. Does the central atom carbon have an octet? No. Uh-oh. So what am I going to do now? I can't just throw a bond in there, can I? No, I can't, because you know what? I have no more electrons. I can't create electrons and throw some in there. I can't do that. That's going to give me too many electrons. All right, so what else are we going to do? Well, this is all I've got. I cannot add more electrons. Oh, I can rearrange them because the carbon's like, I don't have an octet. Who's got something they can share? And oxygen's like, well, okay. So let's move this pair over, shall we? All right, there we go. Oh, now does that mess up oxygen though? It's like, well, oxygen just shared. Does that mean oxygen's not going to have an octet anymore? Well, yeah, it still does. Here's 2, 4, 6, 8. Woo! Oxygen still has an octet. Whew, shoo, that's good. All right, well, you know, carbon's saying, hey, I got 6. Yes, it's still short. So now what's going to happen? Oh, the other oxygen's like, oh, fine. All right, so let's move that pair over. There you go. Now, this oxygen also still has 8. The other oxygen has 8. But what about carbon? If you count them in carbon, what do we have now? It has 8. 2, 4, 6, 8. Woo, everybody's happy. And that's how we do multiple bonds. So when you're doing multiple bonds, you move the electrons around. Don't just add in more electrons. Okay, move the runs around that you have. And you only do that when you get to 0 left over. Don't try multiple bonds or any earlier. Okay? All right, make sense? All right, well, let's see if you can. Yeah, no doubt about that. All right. Okay, here's HCN. Let's see if you can do that one. So did you decide which one was the central atom, right? Yeah, which one is it? Carbon. And then you added up all the valence electrons? Yeah, so 4, 5. Carbon has 4. What? Hydrogen has 1. Hydrogen has 1. It's group 1A. Carbon has 4. Nitrogen, what group number is nitrogen? 5. We are reading the group numbers, right? Okay. That changes the number. That's 10 electrons, right? Okay, so how many valence electrons altogether did we sum up? 10. Has everybody got 10 electrons? Okay, then you put in the bonds. Subtract the bonds. Complete the peripheral. Left over go where? On the central atom. Okay, so leftovers go on the central atom after you've completed the octet. So, let's see, you had what, 10?
12.
How'd you
It's
get
10.
12? It's 10.
Yes,
Yeah, it's 10.
Hydrogen has 1.
Hydrogen's 1? Carbon's 4?
And then nitrogen is 5.
Nitrogen's 5?
So that's 10.
That's 10. So that's going to change
still
your
keep adding
structure a
to
little
it?
bit.
Keep thinking
So
about
10.
the other thing, yeah.
There you go. So did you add up your 10? Okay, so you put in a single bond here.
So that's in,
Why did you do that? You can't do that till you get to 0. Remember? No.
Oh, that's right,
bonds.
okay.
Well, you can't jump to the step 5. You're just going to stay
so that's 4.
step 3. Okay, so that's 6. Then go to step 4. Yeah, keep going. Okay, that's 6 minus 6. That's 0. Okay, now you're to the 0. Now you can think about multiple bonds.
Okay.
You have to get to 0 first. Okay, and then look around and say, hey, carbon needs more electrons. Where are we going to get them from? There you go. So move one over and see if that does it. If not, check again. Okay, how are we doing? Did we get it? Yes? Okay.
It will be 10, so that will be equal to, so you do triple one?
Because you have to move some over. Yep, perfect. Perfect. All right.
Yeah, that's something. I just erased it from there. That's all I just.
Is it the final one forced triple, right? Yeah.
Nailed it.
I was getting there.
I'm gonna get this thing. Okay.
Yeah? All right, how we doing?
I was asking her how come nitrogen has 4 and hydrogen
Because when you complete the octet, hydrogen only has 2 electrons. You can't give it 8. So you can't do that. Right? And remember, you only had 10 to work with. Okay, so how does our structure look? We had an H, line, C, triple bond, N, and a lone pair, right? Woo! Okay, we did multiple bonds. Yay! Well, let's try one with an ion. We haven't done an ion yet. Let's do that one. Let's do one like iodine and bromine, and let's do that one. We'll do Br2 plus. Ooh, plus. You know what that means, right? You're going to take 1 less electron away, right? Because it's positive. We lost 1. If it was a positive 2, we lost 2. Positive 3, we lost 3, right? Okay, so do that when you're summing up the valence electrons and see if you can draw that Lewis structure. Okay, how are we doing with our Lewis structures over here? You doing okay?
Good. It's coming along.
Okay, you know that hydrogen can't be central. Carbon's always a central.
Yeah, Tam took care of that one.
Okay, good. Right, remember carbon.
Voice of reason, yeah.
Yeah, because hydrogen only ever
You see,
wants
the
one
thing was, I
bond.
wrote down the rules as they were on the board, and I still forgot. I was like, wait, how did this happen? I'm like, what happened there? So,
Okay,
and then,
all right, make sense?
Yep.
Okay,
it's coming along.
all right. So how many total electrons did we end up with, by the way? 20. It's one iodine has 7, bromine has 7, another bromine has 7, so that all adds up to be 21. Now it has a positive 1 charge. So what does that mean? You take away 1.
So you do at the end after you add a molar?
Yes. So no, because then it wouldn't be a plus 1. It would be if it was a 1, yeah, it'd be a plus 2 or plus 3 if you had for each. It's not a plus 2. It's not a plus 3. It's only a plus 1. So does everybody see that? It's a charge of 1. This is like a polyatomic ion. It's the charge, it's a plus 1 for the whole thing. So you sum them all up first to get to 21, and then it's a positive charge. You took away 1. All right, so does everybody see how many valence electrons we have? Is 20, right? Okay, then draw your central atom, then the bonds, then the peripheral, and then left over on the central atom. Okay, so draw your skeletal structure, put the bonds in, count the peripheral electrons, left over on the central. You have 20 electrons, and you took away 2, 4, minus 4, yep, that leaves 16, and then you got to complete the octet. So keep going, you got 1, 2, 3, 4, 5, 6, 7, 8, do the same thing that side. 2, 3, 4, 5, 6, 7, 8. Okay, how many dots did you just use up? Okay, minus 12. Where those are left over on the central atom as pairs. Yeah? No, as pairs. 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 That's only, you got 4, you only put 2. Where's the other? There you go. right? You had 4, so you got to put 4 on there, right? 4 dots. Okay, you still write that positive sign because it's still an ion, but you put the brackets around it. That means there's 1 electron less in the group, right? Okay, so does it look like that? Did you guys get this for your structure? Yay! Okay, awesome! We could draw these Lewis structures. Yay! Yippee! All right, well, as we draw these structures and follow this process, there are times when you might have a choice of structures. Following all the rules, you might have a choice. So let's go back and look at CO2 again. Okay, so we had CO2, right? We remember that. We had carbon, single bond oxygen, and then we said oxygen had 6 electrons around that. Okay, now we have a choice where he said, oh, we can move electrons from the oxygen on either side. We could do that. But maybe we didn't want to do one from either side. Could we have done both from the same oxygen? Perhaps. So you have an oxygen, triple bond, carbon, single bond. It fits all the rules. It fits all our Lewis structure rules. And then our other choice would be carbon with our double bonds to each oxygen, which is what we were originally thinking. Yeah, that's got symmetry, doesn't it? But let's ignore this symmetry and pretend we forgot that part. So we're thinking, wow, how am I going to tell the difference between these two choices? The way that we're going to do that is with formal charges. Now, formal charges are not real. They're pretend. Okay, formal charges are fake charges. Okay, they're fake charges. What happens, we would say, oh, well, let's pretend all the electrons got divided up equally and see what the formal charge would be. Now, you can memorize the calculations for formal charges using the formula in the textbook if you want to, where it's the valence minus the bonding electrons divided by 2 plus the lone pair electrons. You can memorize that formula. Or I'll show you another way to do it where we count up the electrons, just counting it up. Okay, so I can show you both methods and you can choose the one that works for you. Now what we want to do is figure out the formal charge for each atom. And how does the formal charge help us decide which structure is the best? Well, we like our formal charges to be as close to 0 as possible. So as many zeros as we can get, that's going to be better. And if we have any negative charges, then we would like those to be on the electronegative atom, right? That makes sense. The negative charge on the electronegative atom, on the more electronegative atom. So let's see how we're going to calculate the formal charge for each atom. So you can use the formula that's in your textbook, or we can take the counted electrons. So let's do that one. I'll show you how we do that. So let's start with this one. If we were to split up all the electrons, let's say this carbon and this oxygen, it's like, ooh, we get a divorce, right? We're going to split up all the assets. Okay, so they have 3 bonds. So we're going to break those 3 bonds and split them up. Okay, so remember, each bond is 2 electrons. So if I'm splitting that up, each atom gets 1 electron out of the pair. Okay, and then let's split this one as well. Okay, so I split this one. So each atom gets 1 electron out of the pair. Now all we have to do is count up the dots around there. So what we're going to do is we'll do the formal charge for this one, oxygen, and we start with the valence electron. So how many valence electrons does oxygen have? 6. Okay, so the formal charge for this oxygen, would be 6 valence electrons minus, now how many electrons can you count around that? 5. 6 minus 5 equals a positive 1. This has a formal charge of positive 1. Let's do the next atom. That's carbon. Formal charge. Carbon has how many valence electrons? 4 minus, let's count all the ones around the carbon. And what do we have? 4. So that's 0. Then let's do this one. Oxygen again is 6 minus, and then I count all the ones around there. And what do we get? 7, so it has a negative 1. So this was a 0 and this was a negative 1. Those are my formal charges. Now let's do this one with the double bonds. Again, we split up all the bonds. Okay, divide our assets equally. Let's do the formal charge for oxygen. That would be 6 valence electrons minus, okay, you counted all the ones around it? Yeah, 1, 2, 3, 4, 5, 6, right? 6 minus 6, that's a 0. Now let's do that carbon. We said 4 minus, let's count them all around that carbon. 1, 2, 3, 4, okay, that's 0. So these have 0, this has 0, and let's do this oxygen. 6 minus, again, let's count all the ones around there. 6. So this has a formal charge also of 0. So looking at the formal charges, plus 1, 0, minus 1, or 0, 0, 0, which one has more zeros? The one with the double bonds, right? So this is the preferred structure. Okay, so you see it makes sense how we did the formal charges? Okay, so formal charges help us determine which is the best Lewis structure. All right, now this just for practice, tell me what is the formal charge for bromine here? Okay, we already drew the Lewis structure, so now I want the formal charge for bromine. Give me the formal charge for bromine. See, what would it be? How would you figure it out? Okay, so we're going to split this, right? Okay, so we're going to count the electrons around it. How many? What's the valence number? 7 minus 1, 2, 3, 4, 5, 6, 7. So it's going to be a formal charge of 0. So the formal charge of bromine is 0. So if you're looking at IBr2 plus and I say, hey, give me the formal charge of bromine, you're not going to say positive 1, are you? Because that's not the formal charge. That's the charge of the whole thing. It's not the formal charge of bromine. So you wouldn't say that. You would have to draw the Lewis structure out, wouldn't you? And determine the formal charge to be 0. So this bromine has a formal charge of 0. What about this bromine? What's its formal charge? Yeah, because we split that bond, and it is also 0. Well, what's the formal charge of the iodine then? Yep, it's, well, let's see, is it? So what's the valence for bromine? The valence is what? 7 minus, and then how many electrons do you count around the iodine? 6. So what is it? Positive 1. So that's a positive 1. Those are the formal charges. Now, you notice the formal charges will all, if you've done them correctly, they should all add up to be the charge. So they do. 0 plus 1 and 0 is a positive 1. And this, CO2 has no charge, so they should all add up to be 0. Plus 1, 0, minus 1, yep. Or 0, 0, 0, yep. So we did that correctly. They all add up to be either the charge or the ion. Okay, makes sense about formal charges? So that's a thing that we can do with resonance structures, is formal charges to help us decide which structure is the best one.